at the University of Salerno, which is like 200 kilometers far from Rome, which is in the middle of Italy. This is our campus, just to tell you where I'm working. This is the laboratory, our laboratory, structural engineering testing hall that you see here in this yellow box. Basically, it's where we perform a lot of testing and we perform some analysis of structures in seismic area. So I'm currently working, as I say, as associate professor. I'm also honorary appointed professor at the University College of London. I was visiting Nagoya for a few months 1 year ago as a visiting researcher. My background is mainly focused, as we know, on seismic engineering. So I'm very pleased to have the opportunity to explain a little bit about the design principles. I'm still working in a lot of research activities. These are some of the projects, but maybe if you are interested, you can also find some of the results of this project on the website of the ECCS, which is the European Convention for Steelwork, in particular the project Freedom, which is from 2015. I'm very happy that I will have also the opportunity starting from this year to share a research activity with Kurbats, so with Normund, Jans and the studio in a project that we will start in October. We were discussing before. We got a lot of prizes with our thesis and our students. I'm very happy to publish our research and to present a lot about our works. I'm currently involved in these classes that you see here. So I'm mainly, my background is based on steel, but I'm still also holding a course of structural design, which is more about the design of reinforced concrete structures, and structural rehabilitation, which is mainly focused on masonry structures. So we have a large background in publication. A lot of them are related to the topic of resilience. And we have a high number of scientific papers. Since some years, 2020, I mean, also in the top 2% list of researchers, and currently involved in some code committees, like the TC10, which is about Eurocodes, so the design of connection mainly. And at the national levels, I'm involved in the committee for the design of composite steel concrete structures. So the topic of today is mainly related to seismic. So I will give you first a short introduction, and afterwards I will present three main topics related to the hazard, reaching the topic of structural dynamics, and afterwards the topic about the strategies to mitigate the seismic hazard. So for what regards the topic of today, what we know is that the earthquake is a particular type of load because it is involving ground shaking. So it's not like the other load types that we're used to manage in design. So let's say that normally we focus a lot in design, so on the static loads, so gravity loads or wind loads. Wind is still dynamic, but we model it like an equivalent static force, typically. But the difference between the earthquake compared to other loads is that this is a load which is applied in the form of a displacement at the base of the building. Displacement, velocities, and acceleration at the base of the building. What is happening in case of a seismic event, which is making this type of load different from all the others, is that normally we activate with this with an earthquake inertia forces in the structures. So inertia forces are those forces which are related to the mass. So obviously, if our building has a mass, the inertia forces will be given by the mass multiplied by an acceleration. And by definition, an inertia force is a force which is acting in the direction opposed to the direction of the motion. So meaning that if the soil is moving on the right side, the building, the inertia forces will act on the left side, as it is depicted in this image. And obviously, since there is also an eccentricity, these inertia forces will be the cause also for some overturning bending moment. So let's say that a ground motion, an earthquake, will be regarded as a displacement type load, meaning that this is applied at the level of the foundation of a building, making it very different from other type of loads, which normally are applied in terms of effect directly on the structure. Like, for example, a wind load, it will be resulting pressures which are applied directly in of a facade of a building. Normally, this is important to say because this will be the result of what we will present mainly today. Even if the ground motion is a displacement type load, so as I said, meaning that the soil will move back and forth during a seismic event, we will try always, not always, in the example of today, let's say, we will try to present the way of designing based on the idea that we are representing the effects of a seismic event in terms of equivalent forces. This is not the only way, but this is one of the main concepts that is very useful for a basic understanding of seismic design. So, of course, when we are talking of seismic, we have effects which are inside the building, which are outside. So the displacement will result basically in acceleration for all the objects that have a mass. So it is very important to focus on the inertia forces and to understand how this can affect the motion of the structure and the stresses which are acting in the structural elements, in the main load-bearing elements. So this is the outline of my presentation of today. I have three parts. So first part, which is mainly related to the definition of the hazard. So let's say how to predict the effects of a seismic event on a statistical base. So of course we know that we cannot know what magnitude a seismic event will happen, but let's say that from a statistical perspective, normally we are able to define the hazard of a seismic event. So let's say that we use a probabilistic approach. Afterwards, I will present some examples and basic benchmark cases to explain a little bit what are the basic principles of dynamics, so the foundation of the seismic design. And afterwards, I will present briefly some of the strategies that can be used to mitigate seismic design for seismic effects, so to improve the performance of building. Mainly going to have a focus on the idea of having some ductility in the structure. So we will see that ductility is a very important feature for a building which is designed in seismic area. And therefore, I will present some of the main aspects related to how we can manage to have some ductility in the structure and why this is important. So going to the first topic, so the definition of the hazard. Of course, we start a little bit from far away, but of course we know that the occurrence of an earthquake is the result typically of a movement of the soil. So normally this movement of the soil is happening based on the theory of the plate tectonics in the area of the world where mainly we have boundary between different plates. Normally along these boundaries we have fault lines, which are just the result of the movement of these large areas. So the areas where we have the boundaries between the plates that we have on our planet. This is based on the theory of plate tectonics of Wegener from 1912. But what we are interested in mainly is not the geological perspective that indeed we already know, but is mainly what is happening when one of these fault lines is moving. So normally we have different phases which are related to the movement of the fault line and so the occurrence of a seismic event. Normally we have a phase of accumulation of energy in a fault line. So energy which is accumulated in the form of elastic strain energy in the rocks. since the rocks are brittle, at a certain point, these rocks will break. The result of this failure of the rocks locally will result in a movement of the fault, and the movement of this fault will radiate some energy. So normally we terminologically we provide some definition which are given here in this slide. So typically we will talk of the focus as the ideal place of origin of an earthquake inside the ground. Of course, we know that there is not exactly a point, but it's more like an area where the earthquake is starting. But let's say that conventionally, this is the place where the maximum spread of energies is happening. Above the ground, normally we will refer to the epicenter as the location which is located above the focus, where we normally have the maximum effects. So let's say that in this point we expect to have the maximum damage in the structure, so in general, but as far as we are talking of building in the structures. And normally we will refer to earthquakes categorized in terms of depth. So of course it's important to know the intensity of a seismic event, and we will see how the intensity is categorized. But also the depth of a seismic event is very important because, of course, we can have an event which is more superficial or more deep based on the distance from the ground of the focus. Normally, we refer to superficial seismic event when these are within a depth of 70 kilometers from the top of the ground. Deep when it is larger than 300 kilometers, and intermediate when we are in the middle of these two quantities. We have to consider that normally a superficial seismic event will cause, let's say the same magnitude, more damage in a localized area, in a more localized area, compared to a deep event of the same magnitude. So normally when the events are more deep, typically the effects are spreading along a larger area. And the fact that everything, and so the energy is also spreading along a larger area, is implying that basically the same energy is transferred, is distributed in a larger part of the ground, reducing the effect that this will have on the structure. So even if a deep event normally will affect a larger area, normally the energy will be also spread in a larger area, reducing the effect of this seismic event. A superficial event, indeed, on the other side, will affect a smaller area, but normally having larger effect in this smaller area. This is one of the considerations that we can do, and it is confirmed by a lot of observation of old or more recent seismic events. It is very useful to look at the earthquake in terms of energy. This is a concept that we will recall afterwards, because when, let's say that fault line is moving, this energy, some energy will be radiated from this source. So this is the energy which is needed mainly to break which is accumulated in the rock, and the energy so that is needed initially to break the rocks. But this energy will be divided in three contributions. So a part of this energy will be lost because of heat dissipation. A part of the energy will be needed to move physically the fault. So it's the work done to move the fault of a certain quantity, so to apply displacement to the soil. But the part in which we are interested is the part related to the waves and the energy which is distributed in the soil and at the surface level in the soil in terms of energy. This is the part of the energy that we will be possibly transferred to our buildings, and this is the part of the energy that we have to care about a lot. So this energy will be needed. We will need to somehow dissipate in some way, so that our structure is able to survive to a seismic event. Normally, the wave energy, the waves, so the energy which is spreading in terms of waves, can be subdivided in three types of waves, as you see here in this diagram. So normally we have body waves. So these are waves which are propagating in the volume of the soil, so in the body of the soil. Normally we have two types, so P and S waves. So P and S can mean two different things, but the same things in reality. So P can mean pressure or primary waves. These are waves which are distributing in the soil, which are passing through the soil and moving in the direction of the wave. So the fluctuation basically is applied in the direction of the wave itself. Shear wave instead is a wave which is applied transversely to the direction of the wave itself. Then we have surface wave, which are different from the former because these first two, primary or secondary pressure or shear waves, are body waves, while a surface wave is just a result of the reflection of these body waves on the surface of the ground. So this surface wave basically will be mainly applied, let's say, in a 2D plane, let's say on the surface of the wave. Typically, the arrival times are different. So as you see from this diagram, normally the pressure waves are faster than the shear waves. So the first are dependent on the modulus of elasticity of the ground, while the second one are dependent on the shear modulus of the ground, and the surface waves are the last arriving normally. So in terms of magnitude, so most typically we have different scales to measure the magnitude of an earthquake. So the most typically used in Europe, but also in the US. When I've been to Japan, I discovered that they use a total different measure, a different scale for measuring the intensity of an earthquake. Of course, as you can understand, there are different ways to measure the intensity. Some of them are based on a subjective evaluation. This is the case, for example, of the Mercalli scale, which was proposed by Mercalli, which was a seismologist in 1902. The idea of this scale is that this is based on the measure of effects. So it's going from a level 1 to a level 12 based on the effect that we will observe mainly after the earthquake or during the earthquake. So let's say that normally a medium intensity earthquake is, let's say, number 6, which corresponds to the fact that this earthquake is felt by everyone. So as you see in this scale, we have terminologies, also terminologically, some words which are felt, feel, not felt by person or felt by person at rest on upper floors. So the problem of this scale is that this scale is not objective. So it's based just on the perception that we have of a seismic event. Also, in terms of vibration or in terms of damage, as you see for the higher level of this scale. So of course, when we arrive to level 12, this means that the damage is nearly total. So basically, there wasn't in the history never an earthquake of the 12th degree of the Mercalli scale. On the other hand, we have the Richter scale, which is correlated to the energy at the focus. This scale basically is based on the definition of a local magnitude, so which is corresponding to an objective measure. Basically, this magnitude is derived based on the amplitude which is recorded at an accelerometer which is placed at a conventional distance. So as you see in this definition, so a magnitude 0 corresponds to a seismic event generating 1 micron of amplitude on the accelerometer, which is conventionally placed at 100 kilometers far from the epicenter. Of course, we never have an accelerometer which is exactly far 100 kilometers from the epicenter, but we make correlation to define this magnitude. So the important thing to underline is that the magnitude is correlated in a logarithmic way to the energy. So this means that the scale is nonlinear. So starting from 1 to 9, the increase of energy is nonlinear. So if we pass from a seismic event of 6 to 7, as you see, this is corresponding in terms of equivalent TNT, in terms of a measure of energy, to 60 million kilograms to 20 billion kilograms of TNT. So the increase of the energy is nonlinear with magnitude. Okay, so in this scale, it's very important to underline this. So it's a big difference having an earthquake of magnitude 5 or magnitude 6. or magnitude 6 or magnitude 7, it is not linear. From a seismic design perspective, what we need. So it's not very important for us, or maybe not too much, to focus on these scales. Doesn't make real sense for an engineer, or at least a seismic design engineer, so as a building engineer, because what we need, in practically speaking, as you see in this diagram, is normally the recording in terms of acceleration, velocity, and displacement at the site where we are planning to design a building. So normally we are not interested in the magnitude. We are not designing a building starting from a prediction of the magnitude. Normally, we are very interested in the acceleration, velocity, and displacement, which are expected to occur at the base of our building. And most of all, we are interested as well in the peak values of these quantities. So if we take the accelerogram, so the diagram depicting the acceleration versus time, we are a lot, as you will see, interested in the peak values of the acceleration, for example, but also eventually of the velocity or of the displacement, which are, we have to underline, not acting exactly at the same time. They will happen in a similar time, but not exactly in the same time. So this is, for example, the El Centro ground motion in California that you see in this slide. Okay, so we're not too much interested about magnitude, but most about this quantity, so acceleration, displacement, and velocity. So what we will find in a code, in a typical code. So we have to say that Eurocode 8 is not applying in all European countries, as we were discussing also a few minutes ago with the Normunds and Jans. For example, in Italy, we use our own code. We are not using Eurocode 8. So Eurocode 8 is like a second level code for us. So first of all, if you're designing a building in a seismic country, pay attention to the local law, because not all the countries are using Eurocode. Nevertheless, these principles which we have in Eurocode, we will find anyway in all the seismic codes around Europe. For sure, if we are designing in a seismic region and each country in Europe must comply with these rules, it is necessary that a reference value of what we call peak ground acceleration, so the peak value of the acceleration that we record during a seismic event, has to be given in the code. Particularly, as we will discuss, there can be some soil effects. Normally, the acceleration is not the same at every site. It can be affected by local soil condition. So typically, this acceleration has to be given referring to what we say a ground type A, which we will discuss this more in detail, is a rock or a rock-like soil. So it's a pretty hard soil. So this is the type of soil for which we expect to have the minimum amplification of the side effects of the acceleration, let's say. Therefore, in the Eurocode 8, in the national annex to the Eurocode 8, we must found this definition. So we must found an acceleration expected at the ground. But as we have said before, seismic event is not something that we know in a deterministic way. So we will never know what time and where a seismic event will happen. Therefore, this peak ground acceleration will have to be defined on a probabilistic, sorry for the grammatical mistake here, but on a probabilistic, in a probabilistic way. Normally, we make reference to a target probability of exceedance of an event, and normally this will be 10% in 50 years, which will be used as design-based earthquake for the no collapse condition, we will call this. So in terms of hazard, we can define typically different probability of exceedance for a time span. So fixing the lifetime of a building, for example, or let's say the probability that we want to evaluate in a certain period, this is more correct as a definition, we can define a probability of exceedance and the corresponding peak ground acceleration. This will result in practical design in different values of the average return period. So the average period for which we expect to have in the reference time frame a seismic event of that magnitude. So normally we can define different return periods based on the intensity. So higher return period will correspond to higher intensity. In the seismic codes, also in the new Eurocode 8, we find 4 levels of seismic intensity for which we have to comply with in seismic design. So level 2 will correspond to a seismic event with lower intensity than level 4. This is important to know, but it's important also to underline that to each of these intensity, we will have different performance objectives. So for what we call the operational or fully operational seismic event, which is a pretty frequent seismic event happening every 45 years or 95 years, as you see from this slide, we expect to have a structure which is performing basically without any damage in elastic range. For higher intensity earthquakes, for example, the life-safe or the near collapse earthquake, what we expect to have, as you see also in this slide, is that typically the structure has to survive to the seismic event, even if with some damage. So a very important thing that I have to underline from now is that when we are designing a building in seismic area, we can design eventually also this building to remain elastic, even for strong events, but normally this will not be economically feasible, meaning that the code is allowing us as seismic design engineers to accept damage in the structure. So in terms of codification, in terms of what is allowed for us to do, typically for frequent earthquakes, so fully operational or operational, as I said, normally the structure has to be with no damage or with very low damage. So there is a more precise definition of what we expect to have from a very low damage or no damage in the code. But for the design-based earthquake, which is the one here in this red frame, or for the near collapse earthquakes, which are rare or very rare seismic events, so happening every about 500 years or 2,500 years, we expect to have some damage in the structure. And indeed, in the near collapse limit state, we expect the structure to be strongly damaged. The important in these 2 levels basically is that we save human lives. It's not important to save the building. The building can be also demolished after a seismic event, but we have to allow the people to survive. So we have this concept, which is called performance-based design. So we have performance objective for different level of seismic event. So we have to comply with this. So in terms of, so if we are depicting the behavior of the structure in terms of base shear force, displacement, let's say performance measure, a bit general here, but let's say displacement. For the fully operational, we expect that we are at the elastic limit. For the damage limit state, we expect to have some plasticity, so some nonlinear behavior, but not too large. For the life-safe seismic event, we expect to have some damage. For the near collapse, let's say it's not exactly how it is in this slide, a little bit dramatic, but we expect the structure to still survive with a residual capacity to bear gravity loads. The important is that people have the time to escape from the building and survive. This concept has to be very clear because this will represent the base of seismic design. So in terms of hazard, probably you are already aware of this. So this is taken from a website. Let's say that the model of the seismicity are basically cataloged and they come from geological and seismological studies. So typically every country will have to be subdivided for the 10% probability of exceedance in 50 years. So this is the design-based earthquake happening on average every 500 years, almost about. This is the case of Latvia. So you see that you have a PGA of just 0.2 meters per square second, which means 0.02 G. If we go to Italy, so if you are designing something in Italy, you will realize that this is becoming much larger. So let's say that we have in Italy a number of seismic area, which more or less are divided in 4 classes. So red is the worst, of course, and green is the better. So the 4th zone that you see here, the green one is basically the areas which in the old times were considered non-seismic, totally non-seismic. the higher seismicity is happening in this area close to Slovenia, or in the middle part of Italy, where we have the most dangerous fault line and where we have normally the most dangerous seismic events. In Salerno, I should be quite safe, as I have to say, because here we are more or less in between the second and third seismic area, more close to the second. It's around 0.1 G, the design PGA. So let me give you now some principles of dynamics. Just this allow me to introduce some concepts like the period of a structure or the damping or the basic concepts which are related to dynamics that allow us to explain and have, let's say, a wider view on the principles which are at the base of the seismic design of structure. Also to introduce the basic design approaches like the equivalent static force method. So I am presenting in these slides some examples which are related to systems which are characterized by single degree of freedom, we say. So a system which is characterized by a stiffness, so a unique stiffness, for example, like in this cantilever element, a flexural stiffness, and a mass, which is normally lumped in one point, like you see here. So this because the motion of this system can be described by a single parameter, which is this lateral displacement. I'm talking about the single degree of freedom system because what I say to this, refer to this system, can be extended to all the other systems. So these are examples of real or almost, let's say, real single degree of freedom system. These are not exactly single degree of freedom, but they can be regarded from the dynamic point of view as single degree of freedom system. So in seismic design, we have three basic quantities. One is the inertia force, as I said, so the mass multiplied by the acceleration. But we have other two quantities, one that you already know for sure, in any case, which is what we call normally the resisting force. The resisting force is just the elastic force that the structure is opposing to displacement. So if we are thinking at a structure which is elastic, this is like the elastic law of materials, so like the Hooke law. So it's just explaining as a relationship between the force and displacement, which is linear, so characterized by stiffness. So of course the behavior can be linear and non-linear. I'm focusing much on linear in this presentation, but we will say something also related to non-linear. So the resisting force normally can be expressed as a displacement multiplied by a stiffness. Stiffness depends on the structural typology. So you see here two very simple examples, but I don't have to focus too much on this. So we have inertia, we have the resisting force of the structure, but we have also a quantity which is very important, which is the damping. So the damping is the force, as you see here, which is related to velocity in a system, which is basically able to slowly fade away over time and stopping the motion of a structure. So even if the structure is totally elastic and there is no energy dissipation given by any other source, damping is the quantity that will stop the motion in any case. So please consider that inertia is a mass multiplied by an acceleration. The resisting force is a stiffness multiplied by displacement. The damping force that we normally represent as a dashpot here, as you see, so like a piston, is the type of force which is related to velocity. So the three basic forces that we have in a structure are basically related to three quantities. One related to the acceleration, one related to the velocity, and one related to the displacement. So the equation of motion of a structure can be regarded based on what we call the D'Alembert principle, which is a very simple principle, which is also called principle of the dynamic equilibrium. So we can regard the equilibrium of a structure, as you see here in this representation, putting the inertia force within the other forces. So looking at the inertia force like a fictitious force. So this is like, for example, the equation, the equilibrium that we have in a structure with a force applied. So let's say that we have a force applied here at this point. This force must be equal to the inertia force, the damping force, and the restoring force. So the equation of motion will be easily written based on this equilibrium. mu double dot plus cu dot plus ku equal to p. If the system is inelastic, but I'm not focusing on this, the restoring force will become dependent on the displacement, depending on the hysteresis of the system. With an earthquake, what is changing? Basically, here the ground is moving, so we have a ground displacement, which is summing up with the displacement of the structure. So we have a total displacement that will appear this time in the equation of motion. So this displacement is given by the displacement at the ground level plus the displacement of the structure. So if we write again the same equilibrium, so the dynamic equilibrium, so between the three forces that we have involved, we should write that the summation of these forces is equal to 0, but the inertia force is equal to m double dot u in terms of total displacement, which is the sum of these two quantities. This will result in this writing. So therefore, if we compare the previous equation with this one, we can also see that the earthquake force can be regarded as an effective force, as it is given in this representation. So what is the problem of dynamics when we are with the force in seismic? Given a mass, a damping, or a stiffness of a structure, given the acceleration that we have at the base of the building, basically everything is founded on the problem of solving this differential equation. We are interested in the end in displacement, velocity, and acceleration. Just some benchmark, I will show this quickly to give you a basic understanding and introduce you some basic concept. And then we go to the result that we need to design a building. So let's see some benchmark cases. So first of all, a case of a single degree of freedom structure with no damping. So the equation of motion that we have seen before, in free vibration, it means there are no forces. So it's just I'm pulling a system and releasing initially, but there is no force applied, there is no damping. So this equation of motion will write in this case in this way. So if we solve this equation of motion, I'm not interested in explaining you how to solve this equation, because for sure you're all able to do it by yourself. Given the initial condition that can be displacement or velocity, what we would observe is that in terms of displacement type curve, this is what we get. So a displacement which is varying during time with a sine cosine shape, like you see here, and the fact that the behavior of the structure will depend on a quantity which is very important for seismic design, which is the natural period of vibration. The natural period of vibration, which is given by 2p Greek over omega, where omega is the circular frequency, is dependent only on a ratio on these two quantities, the stiffness and the mass. And basically the ratio between the stiffness and the mass. What is the period? Is the time it's taking for the system to return again to the same point. So if the period of the system is 1 second, this means that it will take 1 second to start from one point and return again to the same point, which is basically what is given in this slide here. So for how it can look simplified and simplistic, this is what exactly we have in a structure. So every structure will be characterized for a given mass and given stiffness by a period of vibration that will be one of the fundamental quantities that we will need for the seismic design, because the period, as we see, it's affecting a lot the seismic performance of a building. This is an example of a simple calculation for a shear frame, where basically given the mass, the elastic modulus, the inertia of the columns, and the height, we can calculate, starting from this quantity, the circular frequency and the natural period of vibration, which is, for example, in this case, 0.17 seconds. Okay? So for this system, to sway on one side, return on the other side, and go back in the initial position, it will take 0.17 seconds. This is what we can say. Second benchmark. So let's say that still we have no force, but the system has some damping. So we have all the quantities now. So the inertia forces, damping, and the restoring force. If we solve again this equation of differential equation, we again can find everything based on two parameters. So the circular frequency and the damping ratio. The damping ratio is defined as the ratio between the damping factor for our structure and the critical value of the damping, expressed as the product of the natural frequency, the mass, times 2. What are these quantities? So, of course, the natural frequency is the same as I've introduced before. The damping ratio is a factor that is influencing how the motion is stopping. One thing that we can say immediately is that the damping ratio of a damped structure is slightly different from the damping ratio of an undamped structure by the factor zeta, which is the damping ratio. Practically speaking, for typical values of the damping ratio, which is between 0.05 and 0.20 for typical structure, normally there is almost no difference between the natural period of a damped or an undamped structure. You see it from this example, which is the same as before, with a damping ratio equal to 0.05. The natural period of the damped structure is almost the same. So there is basically no difference. So this is now the response of a damped structure. So basically, we have again a sinusoidal motion, but this is stopping over time. We observe that in reality, the response this time depends on the damping ratio. If the damping is equal to the critical damping, this is the condition for which the motion will stop immediately without not even swaying the structure. We have to say that in typical cases, this will not happen. So in a structure, there is always some swaying. The damping is never so large to reach the critical value. And therefore, we have to expect basically that the structural response will be always characterized by a period and by some oscillation of the motion on one side and the other. I leave you in these slides that will be given to you by Norbuns and Jans, this video, which is representing an example about the concept of critical damping, but I'm not showing this to you now. You will find it in your presentation. Now, just other two cases, and then we are done with dynamics. We will go to the final results. So basically, let's see now the same case as we have done in the beginning, but with the force which is applied to the structure. Basically, let's see what is happening when I'm applying on the structure what I will call an harmonic force. So a force which is varying during time with an harmonic shape. So it is pushing periodically my structure in one direction. So with a frequency that I will call now omega, which is different from omega n, which is dependent on the property of the structure. Again, if I find the solution, this is what I will find. If I represent the solution in the diagram of the displacement over time, this is what I will find. The response characterized by what I call the steady state response, this one, and a transient response, which is this one. So in this equation, it will be a transient part. I'm not interested too much in this because this is just a fluctuation around the steady state response. I'm more interested in the steady state response. What I see is that the result, in any case, depends on this ratio, omega or over omega n. So the ratio between the frequency of the force and the frequency of the system. P0 over K, which is the force over the stiffness of the structure, is the corresponding static displacement of the structure. When I'm representing this part of the response in a diagram, what I see is that putting in a diagram the response of my structure as a function of the frequency ratio, so the ratio between the frequency of the force and the frequency of my structure, what I see is that if the frequency of the force is 0, it means that this is statically applied to the structure. So it will return to me, in my equation, a factor equal to 1, meaning that the displacement here is equal to P0 over K, so the force over the stiffness of the structure. But if the force which I'm applying is applied with some frequency, which can be faster or slower, what I will realize is that initially the dynamic response will grow. So the displacement will be larger and larger as long as I am applying this force with a frequency compared to the static behavior. I reach at a certain point an asymptote when when the frequency of the force is exactly equal to the frequency of the structure, and then the response will decrease. Why is that? So let's see what is happening when the frequency applied is just equal to the frequency of the structure. I have an asymptotic shape, meaning that with no damping, let's underline this is with no damping, the response of the structure will increase and increase. I will call this a resonance phenomenon. So when the input force is applied with the frequency which is particular and is exactly equal to the frequency of the structure, what is happening is that basically you have the maximum effects. Obviously, this is in case of an undamped structure. If my structure is damped, this motion will in any case stop, but I will have the maximum amplification. This is a very simple example that you see here, like a simulation of a shaking table test. So if I consider a system which is more slender, so with lower frequency and higher period, based on the frequency of the shaking table, basically I will activate progressively the structure from the lower frequency to the high frequency as long as the shaking table is moving faster and faster. Okay, so not all the seismic events are affecting the structure in the same way. This depends basically on the dynamic property of the system, so their period, and also the possibility that there is some resonance. So this is also another example we have. So I have, sorry, an example. This is an external stairwell for a building where, due to the high flexibility, it was shown on site also due to the human-induced vibration. So you see there is a person at the top of this stairwell which is moving the stair. Basically, how simple can be to move a structure if you move it, basically applying a force, even a small force, with exactly the same frequency of the structure itself. So if you're able to push and sway the structure exactly with a particular period, you will be able to magnify the effect a lot. So you see here that since the structure is quite slender, so basically the period is quite large, it's also possible, for example, to activate large displacement just with the force of a human which is pushing the structure. You see here, okay? This is a very important example which I'm always doing. So this is the seismic event we have in Italy in Rieti in 2016. You see this is the city center of the city of Amatrice in central Italy. We have in this city, as you see in this picture, masonry building. So masonry building are quite stiff. So since they are stiff, it means that they have a small period, so high frequency. And we have in this image, this red building, which is made of concrete, and it is a little bit taller. So concrete will be less stiff and so characterized compared to masonry. More stories will provide higher period to the structure. So basically lower frequency. And we have this tower bell made of masonry, which is more slender. So the period of only these two buildings is larger compared to the others after the seismic event. So obviously the earthquake is equal for all the buildings. The only two things that survived after this earthquake are just the tower bell and this building, because the effects of the earthquake are very different depending on the dynamic properties of the systems. So, going to the conceptual result, of course, when we are in case of an earthquake, still the dynamic properties will be affected by the same quantities, the damping, the frequency of the seismic event, the period of the structure. Basically, what we are interested to do is that for a given earthquake, so a given signal, a given accelerogram, we want to solve this equation of motion to get, at the end, these quantities. So if I'm able to solve the equation of motion, and I'm able to solve it with numerical methods, I can find the acceleration, the velocity, the displacement, velocity, and acceleration in the structure that will give me it at every time instant, the damping force, the restoring force, and the inertia force. These are the three quantities that I'm interested in too. Most of all, I'm interested in the restoring force, because if I have to design the building, I want to know what is the maximum force for which I have to design the building. Therefore, there is this basic concept, which is the equivalent force concept. So, if I know the displacement, I know the force. And basically, I can relate this force to the mass through what I'm calling a pseudo acceleration. So the pseudo acceleration, so since Fs is equal to k times u, while k is equal, as you see in this equation, to the mass times the natural frequency square of the structure, basically I can transform the force during time as a function of the mass. Mass times omega squared times u. Omega squared times u is what I call practically a pseudo acceleration. So the quantity which is relating the seismic force to the mass, and that I can use it very, very easily in seismic design to size the elements. So this pseudo acceleration that will be given to me as a designer by the seismic code is the quantity that I have to multiply by the mass to get the seismic force. Of course, the seismic force will result in a base shear, base moment that I have to use to design my building. So this concept can be extended over time, but I will be interested in reality to the peak of this pseudo acceleration, so the maximum value that this acceleration will experience during a seismic event. Because since there is a linear relation between the force and the pseudo acceleration through the mass, if I know the maximum pseudo acceleration, I know the maximum force, and I can easily design the structure for this force. So it is very important to introduce this concept, the concept of the response spectrum introduced by Hausner and Biot in 1932, which is basically summarizing this idea, the idea of representing through the equivalent force method, let's say for our purpose, the response of all the structure characterized by all the periods in a same diagram. So if I take the peak response, let's say, imagine that we are simulating or testing the behavior of all the possible buildings with all the possible periods, what we get basically is a representation. If we put in a diagram the peak response of all this system, we will have a representation of the pseudo acceleration that I can use as a parameter to seismically design my building in the same diagram. This is the idea of the response spectrum. So we are talking now of elastic response spectrum. An elastic response spectrum will be a representation in a diagram of the pseudo acceleration, so the quantity that I have to multiply by the mass to get the seismic design force as a function of the period of my structure. The period of my structure, let's remember, is that equation that I was showing to you before, so 2p Greek times the square root of the ratio between mass and stiffness. When I'm talking of elastic spectrum, typically I can define different elastic spectrum based on the intensity. So on this spectrum, let's consider that the point that I have for 0 period will be the peak ground acceleration, so the PGA, the parameter that will have to be defined by the code. Typically, as I said, I can define different spectrum. The design spectrum will be the one for the life-safe check with an average period of 475 years, about 500 years. Obviously, these spectra are defined based on a statistical perspective. So it's not deterministic, it's statistical. So we get the hazard, we get the spectrum. This is the spectrum as is given in Eurocode. So it's based on 4 different branches, based on the period. AG is the PGA. S is a soil factor, which depends on the type of soil. So we have to make local inspection, as we will see also today. And eta is a factor depending on damping. So if we put in this equation the typical damping that we consider for the normal design, which is of the 5%, typically this factor is equal to 1. Okay, so normally this is 1 in this equation, or close to 1 anyway. Okay, so as a result, so this is, I'm not going too much into these details because they will be explained also in the next presentation from José. We have in Eurocode 8 2 different types of spectrum, so each country has to decide which spectrum we'll use. Normally for magnitude larger than 5.5, we use the so-called type 1 spectrum, which is one on the top of this slide. For magnitude lower than 5.5, it will be the type 2. This is the classification of the soils. So we have soils from A to E, and we have the very soft soil S1, S2. Normally, A is the harder soil, E is the softer soil. This will depend on the velocity of the shear waves within the soil. So a kind of geological inspection that we will have to do at the beginning. So this is an example. Let's say that we are considering a Eurocode 8, the elastic design spectrum type A, with the PGA of 0.25 G in Italy, for example, with the soil type B, which has a soil factor given in the code equal to 1.2. This is our design spectrum based on the application of this equation, which are given in Eurocode. If we have our structure, the one of the example of before, with this period of 0.17 seconds, what I have to do is to enter in this diagram with this period and read in the diagram the pseudo acceleration, which is, for our case, 0.17 g. If I take this pseudo acceleration and multiply by the mass, I get the force. This force is the force I will use to design my building based on the equivalent static force method. Okay, so something very simple. In the end, all this knowledge, seismology, geology, dynamics, basically it is made very simple because what we have to do is just read an acceleration, what we call a pseudo acceleration, define the force by multiplying by the mass. Let me just say some words. I hope I still have time. I think so. I think I should have still 15 minutes at least. Give me some words to you about the role of ductility. To do it, I want to give this very, very simple example. It is very useful to look, as I said in the beginning, to talk about a seismic event in terms of input energy. So every seismic event will apply at the base of our structure an energy. This energy, practically speaking, if we look at the dynamic of the system, can be transformed just in four quantities. So first quantity, which is the kinetic energy. So the energy related to the velocity, 0.5 mass times velocity squared. Then this energy, which in any case at every time instant will be accumulated in terms of kinetic energy, can be exchanged with other quantities. So in particular with viscous damping, which is the quantity related to the velocity we have said before. Damping will dissipate some of the energy, will stop the motion somehow. The elastic strain energy, which is the energy which is stored in the material, so due to the elasticity of the material, and eventually the fourth quantity, which is hysteretic energy, which is the energy resulting from the damage of some part of the structure, if we want to say this in a simplistic way, from the hysteresis of the material. So let's look at this analogy, which I reported here, which is given in a very famous book of structural seismic design. So the analogy of the building with the retractable roof. So let's say that we have this roof and this building, and basically the rain is representing the input energy to our system. So of course, if the roof is open, the energy can enter in our system and can flow in our system. So initially it will be transformed all in kinetic energy. But during the motion, this kinetic energy can be transformed in strain energy. So the energy which is accumulated in the material and in every time instant, it will be lost in some part due to viscous damping. This damping, which is related to the velocity, which I said before. So normally during the motion, there will be a continuous exchange between strain energy and kinetic energy. And in every time instant, part of the energy will be lost because of the viscous damping. If the level of the water which is accumulated in this tank is reaching a certain level, at a certain point it will be falling down in this other tank, the tank of the hysteretic energy. So basically, if the energy which is accumulated in the material is too high to exceed the material elastic limit, part of the energy will be converted during a seismic event in hysteretic energy. So let's say that looking at the total energy, this can be subdivided in two parts. So a system energy level and an energy dissipated. So the energy dissipation can be viscous damping or hysteresis, nothing else. So there are different strategies. Of course, we can design a structure to be so strong that is able to accumulate the energy during a seismic wave only in terms of strain energy. The motion will stop because of viscous damping. Otherwise, we can also, as a different strategy, decide that our structure during seismic event has to dissipate some energy because of hysteresis. So let's say that this example, which is conceptually very simplified, as you see, something very, very simple, just to explain this to everybody. Let's say that it allows us to visualize the problem in terms of energy, and also to understand that we have different strategies to mitigate a seismic event. So as I said, the strategies can be increase the viscous damping, increase the hysteretic energy, or surprisingly, a strategy can be also to close the roof. So please, let's close the roof so that energy is not entering in our system. What is this idea of closing the roof? So closing the roof means, in our case, looking at the most typical strategies that we have for seismic design, for example, the use of base isolation system. So a base isolation, let's say, is a system which is creating artificially, let's say, a soft story, so a flexible foundation, very flexible in the horizontal direction, so the same direction of the transverse to the building, so the direction of the earthquake, let's say, so that, let's say, the seismic and the base isolation level will act as a filter between the soil and the building, so that action are not transferred anymore to our building. So let's say it's the same concept of the car. So if the wheels are rotating, there is no possibility for the soil to transfer any dangerous action to our car. In this case, we are placing some rollers, some wheels at the base of our building, so that this can move very, very easily. So this strategy of the seismic isolator is one of the most well-known strategies nowadays. Basically, the base isolation system can be realized in different ways with rubber, elastomeric, like let's say, isolator, or friction pendulum, or also other types of isolators. The idea is that we disconnect the soil from the building through the plane of isolator. So the building will not be affected anymore by the seismic isolation. Obviously, the seismic isolation has a cost. Therefore, this is not the only strategy that we apply. You see in this image also an example on how the seismic isolation system can be applied into an existing building. So you see here, this is an example on how the isolator is inserted in a building from the 60s. So it is a reinforced concrete building. So basically the column is cut in two parts, and in substitution of a part of the column is inserted the seismic isolator. But the other common strategies which are used are, for example, the idea of increasing damping. So damping can be simply increased with viscous damper, for example, as you see here. So a viscous damper, basically what it's doing is increasing a lot the term of damping in our structure, meaning that the motion will be strongly limited because of the damping. So you see, this is a very simple example of what I'm trying to explain. There are also strategies which are able to modify the dynamic properties of a building. This is the case of the tuned mass damper, where we apply a large mass around like the 10% of the weight of the building. So maybe this is used as a strategy in many cases to damp the behavior of the structure also in case of wind. This is the case for the Taipei 101. But recently, this building was hit also by a strong earthquake, and this strategy basically was able to mitigate the seismic event a lot. So the tuned mass damper basically conceptually is modifying the dynamic properties of the building to reduce the effect that we have, for example, for the period which are more closer to the resonance. So this is applied in a form of a pendulum with viscous damper that you see here moving during this event. But what is the most common strategy that we apply in practice? The most common type of passive control strategy is the one which is relying on the ductility of the structure, so on the damage and hysteresis of the elements that we have in the structure. So you see in this example, So that we have, normally, we can design for sure the structure to resist to the seismic forces elastically. So basically with no damage. But this is not the only possibility. It is possible always to design the structure even for lower forces, as you see here in this example, force which is lower than this reference force that I should use for the design of the structure if I want this to behave elastically. Since the displacements are not very different, if my structure is totally elastic or plastic, normally what is happening is that the displacement demand which is imposed to a system with lower resistance will be larger and larger. So typically we say that there is the possibility to have a trade-off between resistance and ductility. So you see this depicted in this diagram, force versus ductility. The ductility is expressed as the ratio between the ultimate displacement over the displacement at the elastic limit. So I can decide intentionally to reduce the forces for which I design my structure, for example, from A to B, but as long as I'm reducing the force, the design force, the ductility demand imposed will increase. So increasing the ductility will allow me the possibility to reduce the seismic forces. This concept of trade-off, so reduce the force but have ductility, is a concept that is very clearly appearing in Eurocode, where I have basically two different design concepts. The first concept, which is more useful for low seismic areas. So the concept of designing a structure to be fully elastic. So let's say that I take the elastic spectrum, I take the design forces, use these forces to design the structure. It will be accepted, this kind of concept, which is also said ductility class low, or in new Eurocode it will be said ductility class 1, if the behavior factor that, as I will explain, is the parameter which is summarizing the ductility of my structure, so all a number of phenomena which are related to the ductility of my structure, is accepted to be just lower than 2, or more normally even equal to 1.5. As an alternative, I can design my structure to be strongly nonlinear, so to dissipate some energy, so to have to design this for forces which are lower than the elastic forces. But in this case, I will have to ensure my structure with some ductility. In this case, we call this ductility class medium or ductility class high concept. In our understanding, you have to remind that the larger is the behavior factor, the larger will be the ductility for which I have to design my structure. So using a large ductility factor will allow me to reduce the forces, but then I have to design the ductility of my building. I will have to be sure and ensure that my structure is sufficiently ductile. Conceptually, if we compare an elastic structure with the plastic structure that you see here represented, the behavior factor, the Q factor that you see in Eurocode, is normally expressed as the ratio between the elastic force and the design force for the inelastic structure, or as you see here, it can be regarded as the ratio between, if we transform this ratio, so the shear force experienced by the elastic structure, the shear force experienced by the plastic structure, or better, the design force, this can be regarded in 3 terms. So the behavior factor normally is composed by 3 terms. A term which is related to the design overstrength, so the ratio between the elastic limit of my structure and the design force. A ductility component, which is the ratio between the elastic force of the shear force of the elastic structure and the resisting force on the nonlinear system, and redundancy and redistribution effect, which is basically the ratio between V1, Vu, and V1. All these factors can assume a different value, as we will see today in different examples. The design overstrength normally is fixed as equal to 1.5, based on the fact that we use in design safety factor and so on. redundancy, redistribution, and the ductility component depend on the structural system. Conceptually, when we design, using a behavior factor will mean that basically we use the same procedure as we have said before. So we apply forces, but we pass from the concept of elastic spectrum to the concept of inelastic spectrum. So we divide the pseudo-acceleration by a behavior factor. So in design, we will use much lower forces if we are able to assure that the structure is ductile at the local and global level. The elastic spectrum is basically equal to the elastic spectrum divided by Q. The Q factor will have to be defined based on the structural system. This is an example that I have here. So let's say that I'm designing the same structure as before with the same elastic spectrum that you see here in orange, but the elastic spectrum that will be equal to the elastic divided by Q is given here in this image. So it's lower than the elastic one. How lower? This depends on the structural system. So let's say that this is a moment-resisting frame. A moment-resisting frame is allowed to have a ductility factor, so a Q factor equal to 5 times this parameter alpha U over alpha 1, which depends on the number of bays and the number of stories. Let's say I'm designing a single-story building, as I've said, 1.1. So 5 times 1.1 means 5.5. So practically speaking, when I'm designing this building, now the force will be not anymore 150 kilonewton as in the previous case, where I was considering a perfectly elastic behavior. In this case can be 5.5 times lower. This means that when I'm designing, most probably using a behavior factor, I will be able to obtain a structure which is more economical in some point of view, but I have to remind that I will have to comply with a number of rules which are defined to provide ductility to the structure. This is the difference. It will be still on some way a force design method, but I have to provide ductility. This will be done with some methodologies that we will see today. So these are some examples. So for C structure, we will find the categorization of the system in different ways. So the behavior factor is a system factor, so depends on the material that we use and the arrangement of the structure. So it's different if we are talking of a frame, of a concentrically braced frame or an eccentrically braced frame. You will see that we find different numbers to be applied. This depends on the ductility rules and hysteresis that we are able to apply. For concrete, you see that you see examples in the presentation of José. So I'm not going too much in details of this, but again, we have the wall system that will have a different behavior factor from the frames. So you see here different numbers which have to be used based on the different field of application. So when I'm deciding what is the behavior factor, I have to know the material and the system. We have here different examples for concrete. I wanted to underline that this is also a question that was raised by Normus a few days ago. We have in the new generation of Eurocode 8 that will come out in a couple of years, 2-3 years, we will have also these typologies which are very widespread in non-seismic areas, I will say, because as we see, these are characterized by pretty low values of the behavior factor, which is the case of the large wall structure or the case of the structure with flat slabs. These are not currently in Eurocode 8, but they will be in the new version of Eurocode 8.8. This is a table from the new Eurocode 8. Where you see behavior factor for different ductility class level. For example, flat slab structures are allowed only for a medium seismicity level, and they are characterized by behavior factor equal to 2, which is quite low. As we said before, 1.5 to 2 is basically almost a non-seismic design structure. For large wall structure, you will find in this slide, based on the definition of this parameter, which depends on the aspect ratio, we can define a behavior factor for large wall buildings, which is between 1.5 and 3. 3 is still not so low, so I think this is also very good to know that in the new Eurocode we will have information also for these typologies which are not currently considered. So I stop my presentation now and give space to the question. I thank you all the audience for this first presentation and attending so having patience with me, and thanks a lot. I give the word to Jans.
Yep. Thank you, Massimo, for great presentation and introduction to the seismic design. We have 3 questions from the audience. The first one, in one of your presentation slides, you showed the seismic hazard map. What is the website address of the seismic hazard map?
Wait a second, because I didn't get a part of what you said. So
I think it was in presentation slide 17.
Homepage address. Okay.
Yes.
You mean in this presentation? You mean this maybe when I was presenting the Drupal? So this is this one, right?
Yep.
I think so. So this is a website. This one. This is from Drupal software. This one. Okay. Drupal.com. Here you find wind, snow, and seismic laws for I think all European countries, or almost all of them. It is a pretty interesting tool because, of course, you just go into on the map, and you will find country by country the hazard map, and also, okay, thank you. I see something in Latin, I don't understand, but maybe you get it. Okay.
Yeah, thank you. I think you answered the question really good. The next question is with regards to the soil types table. These soil types are related to 30-meter thick topsoil layer. What if there's no A-type ground below 30-meter depth? Shall be any amplification considered for the ground below 30-meter depth in this case? Those multiplying the seismic effect.
We have to refer to the average in the first 30 meters. So independently from how the soil is layered. So it is what has to be defined in the first 30 meters. Yes, even if there is a softer soil below a harder soil, let's say.
Okay, and the last question from the audience: do you also use sloshing dampers in Italy?
Never seen one applied, to be honest. So Italy is pretty seismic. Let's say that normally in Italy for the application where we have higher seismic hazard and we have higher importance building, the typical policy is to use seismic isolators. This is basically now is done as a basic policy for hospitals, for example. All the hospitals are currently built on seismic isolators. The other type of dampers, so let's say sloshing damper, I've never seen applied, to be honest. Not in Italy. In Italy, they are very used BRBs or viscous dampers, so hysteretic or viscous. These two are very used in the retrofit of existing buildings, not even too much applied in new buildings. So let's say that for a normal building, typically the idea of dissipating energy by hysteresis is applied. Not very much we use dampers in new buildings. If we have higher importance, we use seismic isolators. In the retrofit, dampers are used a lot. So viscous and hysteretic dampers like BRB. So this is, if I have to say more or less what we are using currently, this is more or less the idea that we have in our mind in Italy. But this is country-based. So in every county, we found different opinions for sure. Okay,
thank you.
Yes, actually, we have some questions in webinar chat as well. Maybe colleagues, you could look in them.
Yes. According to the 2020 European, so if I understand the question from Valeris Nicolins, so I think it's meaning about the spectrum, which is the defining between 0.00 seconds and 5 seconds. Normally it is in Eurocode, this is defined up to 4 seconds a spectrum. After 4 seconds, independently from the period, we have to assume the same intensity. So the SPA at 4 seconds is what we will apply even for 6 seconds, 7 seconds, or 8 seconds. There is a threshold limit. Okay, we don't go below this number. So, but anyway, you find the spectral acceleration in Eurocode 8. There are the formulation to get the spectrum, if I understand the question.
Okay, I think we still have a question, time for one more question. So from my side, if you look globally, there's a tendency for temperatures to increase and water levels to increase. Are there also some tendencies for earthquakes? Are they increasing, frequencies increasing, or maybe opposite?
This is a question for seismologists. So I don't think there is a tendency for earthquakes to increase. So we have a period in Italy we were starting to think about that, especially in the last 20 years, because we have a quite strong earthquake more or less every 5-6 years in Italy. We had in 2009, 2016, 2013. So it looked to be a bit over the expectation that we have, to have more earthquakes than expected, to be honest. But correlating this to the global warming, I don't think there is material to say that. So I'm not sure. What I heard in the last earthquake there was in Bangkok and in Asia, I heard that this earthquake was very strange because the distance from the epicenter and the part where there were strong effects was very large. So like more than 1,000 kilometers.
Okay.
So
What I heard from seismologists that if we are making more measurements, then we can find rising seismicity. Like in Sweden, where they are making more measurements near their nuclear power stations, there they are finding higher seismicities there in places where they don't make any measurements.
So let's say that there are certain countries where there is, let's say, human-induced seismicity due to fracking. So the perforation in the soil, as in Holland, this is happening. They're interested a lot. I don't know if even maybe so normally northern countries, they have this phenomenon. But I think that really in Europe you have to check when you are designing a building because there are some regions where initially didn't expect they were very seismic. Like in Belgium and Germany, there is an area which is also seismic, which is close to the Ruhr in the steel area, let's say. In also Liège is seismic. They have a pretty strong earthquake in 1983. Of course, what is the difference is that maybe the number of events you have is very few. So they happen, they occur just very with a very low frequency. So it's a big difference, I think, compared to countries like Italy, Greece, Turkey. In Portugal, I have no idea when it was the last earthquake. I know the famous earthquake from Lisbon, which is always mentioned, but there are many, I think.
Okay, and maybe some small question from my side. What do be your practical advice on calculation of period of natural vibration of structure? There are some empirical formulas in Eurocode, but usually I suppose we use finite element analysis, but then there are a lot of questions about what stiffnesses of, for example, concrete or foundation should you assume, and what masses, because usually in the vertical construction design we overestimate masses. But if we use larger masses in installation design, we will get higher period, lower frequency. It will be not so safe. What's your comment?
So for the calculation of so I anticipate something that José will say in his presentation, but sorry, José. So for what regards the methodology for calculating the period, you have an empirical formula. So every code has some empirical formula. So in Eurocode 8, but also in the Italian code, there is this empirical formula, which is function of the structural system and the height. But this has to be used just for the pre-design. So just to guess initially what is the size of the element, let's say. When you arrive in a level of the analysis which is more advanced, that point it is necessary to evaluate more correctly the period of the structure, of course, because this is directly influencing the forces that you apply in your structural model. Basically, you have different methodologies. Some of them are analytical, basically. So you have, for example, the Rayleigh method that José will present, which are based on the evaluation of the displacement of the structure under the forces, horizontal forces equal to the masses, let's say. So this is what can be done. Or you can get with the modal analysis of your building. Of course, when you do this, when you apply every of this method independently from the method itself, as you said, it's important to understand that since the period is a function of stiffness and mass, you must predict the mass with a certain level of accuracy. This is a bit conventional. So the mass to be applied is defined in the code. So basically, it is almost equal to the mass that we consider under the limit state in the quasi-permanent combination, let's say. So let's say it's for a typical building is like GK plus 0.3 QK. So permanent plus 30% of the live load. Normally, this is the mass that we consider for a typical building, but this is ruled in Eurocode under different situation. For the stiffness, let's say that depends on the material. Because for steel, normally we don't have a problem. In the sense, or maybe we can have also a problem, but the material itself is not giving a problem in the sense that the modulus of elasticity of steel is 210 gigapascal. Of course, in that case, for some system, we can have some problems because of connection, for example. The semi-rigidity of joints can influence the period of the structure. So also in that case, we have to predict with a certain level of accuracy the stiffness based on the stiffness of the connection. For concrete and masonry, is a bit conventional in that case, because of course you know that this concrete, depending on creep, is depending on viscosity, cracking, and so on. So typically it's conventionally accepted that for seismic purpose, the stiffness of the structure is evaluated using 50% elastic modulus of the material. So EC divided by 2. And then the response is evaluated based on the geometrical stiffness, let's say, of the elements. So it's a bit, it's the same more or less for masonry. Masonry, we also reduce the elastic modulus to 2, to the 50%. And of course, it is necessary to consider the flexural stiffness and shear stiffness, especially masonry, for example. So this is more or less, but
Thank you.
José is also... I'm just disturbing a bit José because
okay.
He
Thank you very much.
In this presentation.
So, thank you very much. So let's have a little break. According to our schedule, we have a 15 minutes break.